Hello students, welcome back. We went through a lot about limits. Now let's focus ourselves upon continuity. Now the continuity of the usual functions are just trivial. They're all continuous. Anything you can think of, they're all continuous. There are exceptions, however, and those exceptions are piecewise defined functions, and that's where we're going to focus upon. Here's an example of a piecewise defined function. It is defined in 3 pieces. First piece, first line, second piece, second line, third piece, third line, and here is the visualization. When x is less than or equal to 0, y equals to x squared minus 2x is this curve blue. When x is between 0 and 1, y equals to negative x squared is this curve, red. And finally, when x is greater than 1, y equals to 2x minus 3 is this line, green. Make sense? Now, apparently this function is continuous. Why? Well, right here at 0, 0, blue and red merge, and right here at 1, negative 1, red and green meet. Of course, in any other x values, there's no way we're going to get discontinuity because x squared minus 2x is a continuous function. It's a parabola. Negative x squared, that 2 is continuous. 2x minus 3, that 2 is continuous. So there's no way that this function can be discontinuous at any other point other than x equals to 0 and x equals to 1. X equals to 0, the boundary point between the first line and the second line, and x equals to 1, the boundary point for the second line and third line, right here and right there, in terms of x value, that is. And do we actually have continuity here? Well, let's check. And how do we check? Simply by plugging in. By the way, this is what we want to check. The function value, the left-hand side limit, and the right-hand side limit must be the same. Most of the time, you don't really have to worry about this part. Only these two matter most of the time, but exceptions do happen. Okay, when x is equal to 0, you have to use the first line, right? Because x equal to 0, that's included in this semi-inequality, not down here. So you have to use the first line for x equal to 0. Now, what if x is not equal to 0, but pretty close to 0, but a little bit to the left, a little bit less? Then it's the first line. So from here, taking the limit, plug in x equal to 0. That's the computation. And when x is a little bit greater than 0, then I have to use the second line. And from there, approaching to 0, so plug in x equal to 0. There you go. And look at all those limit values. They're all the same. So the function value, f of 0, and left-hand side limit, and the right-hand side limit, they're all the same. And the common y-coordinate value is 0. Look at this picture. They're all the same, so we have continuity, and the common y-coordinate value is y equal to 0. All right, we have continuity at x equal to 0. So find all x values at which the given function is discontinuous. Well, we have two candidates, x equals to 0 and x equals to 1, but one candidate is out. The final candidate, x equals to 1, let's check. And you have the picture here, so that 2 will be out. But let's check. Plug in x equals to 1 to the second line. We have to do it to the second line because we have equality here. And then plug in x equals to negative 1 to the second line. We get the left-hand side limit because x is a little bit less than 1. On the contrary, when x is a little bit greater than 1, that's the right-hand side limit. You have to use the third line. So plug in x equals to 1 to the third line. We get the right-hand side limit. So limit 1 minus versus limit 1 plus. They're all the same. And the common y-coordinate value is negative 1, and that's right here. So we have no discontinuity, confirmed by the picture as well. Here's another problem. We have, again, two possible breaking values. X equals to what? -1, and x equals to what? 2. Do you see that? -1 is common for first and second. So that's going to be the boundary point, the threshold for blue and red pieces. And x equals to 2 is common for second and the third line. So that's going to be the boundary point, the threshold between red curve and green curve. Do they actually meet? That's the problem. If they do not meet, then we have discontinuity. We may have jump. How do we get it? Well, we have to plug in the numbers. For x equals to -1, you can plug into the first line and also to the second line because they're common there and see if they are the same. And for x equals to 2, second line and third line. Ready? Well, okay, here's the computation. And x equals to -1, plug in to this, blue, and plug in to the second, red, and if you do your computation, you ended up with 6 equal to 6. Okay, that's right. So the left-hand side and right-hand side are the same. So at x equals to -1, blue and red will merge together. So we have continuity. Make sense? At x equals to 2, how about that? You have to plug into here and there. And is that true? Plug into this, that's red. And plug into green, we get that. And they're not the same. 3/4 is not equal to 2. That means we're going to have a discontinuity at this point. Otherwise, all continuous, so we have only one discontinuity, and that's x equals to 2. Let's check out the graph. Does it fit? Here, 3/4, excuse me, versus 2. So they're different. Over there, they're the same. 6 equals to 6.